At the end of this lesson, the students will be able to understand about electric current, understand about drift velocity, understand about Ohm's law, understand about Kirchhoff's law. Definition of electric current. Electric current is defined as the directed flow of electric charges. The strength of the electric current is measured by the net charge flowing across a certain area per unit time. Thus, the electric current is given by I is equal to Q by T, where I is equal to steady current, Q is equal to net charge, and T is equal to time. Drift velocity. The average velocity acquired by the free electrons in a conductor subjected to an electric field is called drift velocity. Drift velocity is equal to I by NEA, where V is equal to drift velocity, I is equal to steady current, N is equal to number of free electrons per unit volume of the conductor, E is the charge on each electron, and A is equal to uniform area of cross-section. Ohm's law states that the current flowing through a conductor is directly proportional to the potential difference across the ends of the conductor, provided physical conditions of the conductor such as temperature, mechanical strain, etc. are kept constant. Thus, I is directly proportional to V implies V is directly proportional to I. This can be written as V is equal to Ri or V by I is equal to R, where R is known as resistance of the conductor. It depends upon the length, shape, and the nature of the material of the conductor. Thus, from Ohm's law, the variation between potential difference V and current I through a conductor is a straight line OA as shown in the image. Kirchhoff's laws. First law. The algebraic sum of the currents meeting at a junction in a circuit is 0. Consider a junction O in the electrical circuit at which 5 currents are meeting. Let I1, I2, I3, I4 and I5 be the currents and its directions are shown. Let us adopt the following sign convention. The current flowing towards the junction point is taken as positive and the current flowing away from the junction point is taken as negative. Therefore, by Kirchhoff's first law, a junction O minus I1 minus I2 plus I3 minus I4 plus I5 is equal to 0. Thus, algebraic summation of current meeting at the junction point O is equal to 0. Second law. It states that the algebraic sum of changes in potential around any closed path of electric circuit involving resistors and cells in the loop is 0. That is, algebraic summation of delta V is equal to 0. Consider a closed electrical circuit as shown containing two cells of EMFs, namely E1 and E2, and three resistors of resistance R1, R2 and R3. We adopt the following sign convention. The EMF of a cell is taken negative if one moves in the direction of increasing potential through the cell and is taken positive if one moves in the direction of decreasing potential through the cell. The product of resistance and the current in an arm of the circuit is taken positive if the direction of the current in that arm is in the same sense as one move in a closed path, and is taken negative if the direction of current in that arm is opposite to the sense as one move in a closed path. Now, applying Kirchhoff's second law to the closed path ABEFA, we have I3 R2 plus I1 R1 minus E1 is equal to 0. Therefore, E1 is equal to I1 R1 plus I3 R2. Similarly, for closed path A, B, C, D, E, F, A, we have E2 minus I2 R3 plus I1 R1 minus E1 is equal to 0. Therefore, E1 minus E2 is equal to I1 R1 minus I2 R3. This implies algebraic summation of E is equal to algebraic summation of I times R. Note that the above relation is true when there is no capacitor in the circuit. In the presence of the capacitor, the above relation is not correct. Find the drift speed of the conduction electrons in a copper wire of cross-sectional area 1.5 times 10 to the power of minus 6 meters square, carrying a current of 5 ampere. The density of the copper is 8.95 grams per centimeter square and atomic mass is 63.5. Solution. Given the cross-sectional area of the copper wire is 1.5 times 10 to the power of minus 6 meters square. Therefore, A is equal to 1.5 times 10 to the power of minus 6 meters square. Also given a current of 5 ampere, therefore I is equal to 5 ampere. We know drift velocity V is equal to I by NEA, where V is equal to drift velocity, I is equal to steady current, N is equal to number of free electrons per unit volume of the conductor, E is the charge on each electron, and A is equal to uniform area of cross-section. We know that the charge E on each electron is equal to 1.6 times 10 to the power of minus 19. Since the value of I, A and E are known, it is enough to find the value of N and substitute it. We know N is equal to number of free electrons per unit volume of the conductor. That is, N is equal to Avogadro number by volume. We know that the volume is equal to mass by density. Given the value of mass and density, substituting it, we have 63.5 by 8.95, which is equal to 7.09 centimeter cube. Substituting the values in N, we have 6.20 times 10 to the power of 23 by 7.09 times 10 to the power of minus 6. On simplification, we have 8.74 times 10 to the power of 28 electrons per meter square. Substituting all the values, we have drift velocity is equal to 2.38 times 10 to the power minus 3 meter per square. Thus, drift velocity V is equal to 2.38 times 10 to the power minus 3 meter per square. 12 equal wires, each of resistance 4 ohms, are joined to form a skeleton cube. The current enters at one corner and leaves at the diagonally opposite corner. Find the total resistance between these corners. Let the total current entering the cube is 6I. Since the resistances are equal and they are equally divided, let R be the effective resistance between the diagonally opposite points A and G. Then 6I times R is equal to E. Applying Kirchhoff's second law to the closed circuit AEHGEA, we have 2I times 4 plus I times 4 plus 2I times 4 is equal to E. On simplification, we have 20I is equal to E. Equating 1 and 2, we have 6I times R is equal to 20I. This implies R is equal to 20 by 6. On simplification, we have the total resistance between these corners is equal to 3.33 ohms. Find the effective resistance between the points A and B of the network shown. Each resistor has a resistance of 1 ohm. Can you remove 2 resistors from the network without disturbing the current distribution? Solution. Let us connect a battery of EMF V and negligible internal resistance between points A and B. Let total current through the battery be 3I. This current is equally divided among three equal resistors. Let the effective resistance of the network be R. The points C and D are the same potential, so no current flows through the two resistors DE and EC. Applying Kirchhoff's second law to the mesh ADBVA, I into 1 plus I into 1 minus V is equal to 0. This implies V is equal to 2I or I is equal to V by 2. Substituting the value of I in R, we have R is equal to 2 by 3 ohm. Thus, the effective resistance between A and B is equal to 2 by 3 ohm. Since no current flows through DEC, even if we remove the two resistors connected along the path, there will be no charge in the current distribution.